Okay, from some of the questions during last lecture, I decided maybe I should talk about this concept called peer-to-peer system, which is a very dominating paradigm. Probably started at the early 2000s, was really being used a lot in the maybe around 2010. And then after peer-to-peer, then we have a lot of AWS cloud and those things coming up. But still today, peer-to-peer system is still being used, and it will come back, by the way, that this is the same type of idea. As I mentioned, the computer system in the human history is always from mainframe to PC to network computer to cluster, and then to peer-to-peer, and then right now is basically cloud and virtualization is dominating. But in the future, you will not be surprised when peer-to-peer, this kind of concept will start. I mean, even peer-to-peer is still being used, is not as much, but still some of the principle you will learn from this lecture will be applied to a lot of interesting system concept. So what is a peer-to-peer system? So just want to give you a background. You most likely have already been using peer-to-peer system. So traditional system is a client server. So like when we're doing JSON RPC, it's essentially you see that we use a concept client server a lot. Means that the client is actually requesting a service from a server, and the server will reply. So you have this kind of client-server relationship. And peer-to-peer, on the other hand, is more equalized about the role. And a bunch of computers, they actually collaborate, exchange, and such that they will be able to accomplish some purpose. That purpose could be perform some computation, or that purpose could be simply want to share some information. And the enabler of peer-to-peer system really started when the internet is getting more and more popular. So you probably remember that internet was there for a long time, maybe 50 years already. I think the first internet was this 4-node internet in California was first introduced in 1969. At that time, the IP and TCP protocol was being developed. And then in the 1995 or 1994, we started to see the concept of HTTP and web. And at that time, the internet, last time I showed you the growth of the internet, around that time, there was a boost from 1995 and 1998 or 1996, I forgot, Google at that time introduced to the market. So the whole thing is being boosted up about the network bandwidth. And people realize something. People realize, oh, I have a computer. It could be my desktop, it could be my PC, or it could be my cell phone. And a lot of us have a lot of resources, computing resources here and there, and then they're all networked together. And the idea of peer-to-peer computing is that, well, why don't we just leverage using that? So if you have your desktop computer, you contribute some of your network bandwidth, CPU cycle, and the memory. And if everybody is doing that, and if the network bandwidth is actually healthy enough, then we can essentially doing something which is a typical cluster or mainframe computer can do. All right, and that's kind of paradigm. I mean, be careful. This kind of paradigm obviously will not work for all kind of application. But just there is a spectrum of application that you realize that you do have some unused resources to share, either network memory or even hard disk and CPU, obviously. And how do you actually aggregate those resources together to work on something? And that's what we're going to talk about. It's called peer-to-peer system. So in contrast, today's dominating computing paradigm is like a cloud and virtualization. So essentially what they're doing is they aggregate all these resources, which is distributed at your home or your home. And we actually put together in a place which is under AWS. And they have a rack for us to manage and control. So we kind of outsource that control to a particular service provider and let them handle that. But the concept of peer-to-peer is interesting is that not only I'm contributing, I'm actually can control that as well. Because you're part of the node. You're actually on one of the nodes. You can actually see, for example, who you're actually connecting to, their IP address, and maybe even their identifier. And the thing is that we kind of seeing that where the cloud computing model that we have, we kind of trust a third party to do something. And over here, we have to trust a lot of other parties as well. Some of them are probably in a place we have never been to. But as a participant of the peer-to-peer, you also can actually contribute. And therefore, you can actually do something which is more interesting in that way. Okay, so let's actually talk about some of the, I'm actually going to talk about, there are two kinds of peer-to-peer. One is called unstructured peer-to-peer. One is called structured peer-to-peer. So I only want to talk about structured peer-to-peer today. The David social link, the structure I provided last time, it's like unstructured peer-to-peer, to be honest. And because we don't have an infrastructure to helping us to organize things. And now this is a structured peer-to-peer. So what is a structured peer-to-peer? Structured peer-to-peer is really designed to provide scalability. I mean, you can think about a peer-to-peer system. You have lots of peers on the internet would like to participate. I mean, if the numbers are small, it's fine. But you think about what were the earlier application for peer-to-peer, such as Napster, sharing music, sharing. In fact, all the dominating peer-to-peer application to me at the early stage, or even today, is sharing. Sharing music, sharing illegal movies, sharing whatever. All right. So sorry that 95% of the content they share on peer-to-peer at one point at least is actually questionable content one way or the other. I mean, for example, I remember that there was, of course, the textbook is pretty expensive, right? And some of the students just actually upload a scanned copy of their textbook and then share on some of the content, all right? So it's an ethical question. Well, I kind of sympathy for the student because they already have a huge loan they need to care. And the thing is that the publisher are probably make a lot of money out of that process. So I'm not promoting that, but I'm saying that it's a kind of questionable, at least, the situation. So, so now we're actually thinking about, okay, we're sharing content. Then how do we actually decide where to find the right peer who has the content? Okay, so this is interesting. You think about that. We have a network called peer-to-peer. We share our resources, not just network, but hard disk or memory. And therefore, if we talk about sharing content, then the content you like to get must be stored somewhere in one or more of the peer. So a very important operation for the peer-to-peer system is for you to be able to find where they are and try to get that content to yourself because you like to have a music. For example, if it is a piece of music, because typically music are pretty small. So it's probably just you need to retrieve once. But if you want to look at movie, a movie could be 4 gigabytes. And the thing is that you'll realize that this 4 gigabytes, you're going to chop them into chunks. Each chunk is 64 megabytes. And the thing is, each of the peer will host a bunch of chunks, but not the complete movie. So the thing is, for you to actually be able to retrieve the content you really want, then you have to go for a lot of different peer and to grab those pieces you don't have. But once you grab those pieces, you start to offer those pieces as well. Once you have it, right? Then peer-to-peer is kind of, if you want to use the resources, you have to contribute. So there is actually game theory to actually design the protocol such that you will actually get the speed or the resource you want or priority you want based on how much you have exchanged with another peer. So that's a whole economic issue in the peer-to-peer design. It's about exchange of service. It's not just because we're all equal. Okay, so the thing is that come to an issue. So the fundamental issue with peer-to-peer. I suddenly realized I forgot to use my microphone. Give me a second. Okay, can you hear me?
I think you haven't shared the screen.
That's marvelous. Should I restart? Hold on. I didn't hear anybody complain until you. Thank you. So I believe all the students over there, they're sleeping. Okay, they're not listening. All right. Okay, for all of you here, thank you. But hey, remote student, are you sure you're still there? They went to Panera Bread already. All right, fine. All right. I'm sorry. Oh, okay. Now I see the chat. Okay. All right. Just checking. Okay, just checking that you guys are still up. Okay. All right. All right, fine. I'm glad I haven't. This is the second slide. In fact, this is the first slide that's actually make any content. The previous slide just a topic. So okay. I apologize to the remote student, and I'm sorry, but you didn't miss any slide. All right, this is the first slide. I'm still over here. So, so in the peer-to-peer system, a universal capability we need to provide is to find the peer that offer the content you would like to have. Okay, so how do we do that? In a way, you can think about, okay, here's a few challenges. Number one, we don't know how many people will join because you might go to work, you turn off your computer. But when you come home, you turn on your computer. You actually pop in. So this is really interesting because it's trying to grasp as much as this kind of distributed resource together into one single computation, and yet they have to deal with network failure, they have to deal with node on and off, joining and leaving. And yet, how do we actually be able to handle this in a systematic way? So that's the subject we would like to cover. This is called structured peer-to-peer because it has a structure, it organizes all the peer into some kind of structure to allow people to be more efficiently contacting each other. You will realize that if without this idea, the core idea I want to talk about is called DHT, distributed hash table, which without distributed hash table, you can imagine the whole thing will become really, really hard for you to be able to efficiently communicate. Okay. All right, so here's an issue we try to understand. There are two issues I want to say. Number one is you have to actually realize that each peer must have some sort of identity. There is an identity issue we need to deal with. And once you know about your identity, then you actually need to realize what's the routability. Means that, well, you know this, for example, when I joined this particular peer-to-peer service, I could use my email address and convert my email address or some other thing, or maybe even a random number, to generate a unique identifier that's actually allowed me to enter the system. So when I participate the system, I actually have a virtual identity, which is for me to decide where I will be in the peer-to-peer system in the structured way. And then people realize, well, okay, once I want to contact, okay, if you think about that, peer-to say, I have a virtual identity, I'm somewhere, and I tell people, hey, I have this content, this content, this content. And then whoever want to get this content, then they need to route their traffic in some way. I will show you how the routing will work. And then it will reach me so I can give them the content. So the first part we need to worry about is, well, what is a peer identity? And how do I actually provide routing among this peer identity? Okay, by the way, this routing is not what we call network layer routing, not layer 3. It's a layer 7 routing, which is application layer routing. This routing means that, for example, typically routing is you actually talk to your small router at home, your small router go to AT&T, AT&T go, no, this is not that kind of routing. The routing we're talking about is, I want to contact with that guy, I will route it to you, you route it to him or her, and then she will go there. So I want to find a routing that's actually a map, our computer, to find that guy. Once I find my destination, then we're going to exchange content directly. So that's the routing we're talking about. So the routing has two parts: is discovery and exchange content. All right. So the second part is the content assignment. It's interesting that you have to have this capability. So what I'm saying is that, well, if I have a piece of content, where do I actually store it? I mean, this content could be at your place, but I want to actually make sure that certain content will be sent to certain people. So the reason I want to get this, the reason I want to route it to the other corner, that student over there, is because I know he has a content. But this reflects the other issue as how do I actually distribute this content? Why does content need to go to that? There is another issue which we need to work on is the key content assignment. So if you think about, I know you guys are working on GFS right now, and the GFS has a master index server. And the master index server is actually helping us to decide where is the trunk server, where's the primary, where's the secondary. But in a peer-to-peer system, that the structure will actually determine, the whole structure of the peer-to-peer is actually acting like a master index server, because the whole structure actually has information about who actually owns what. Okay, so the thing is that there are a few examples. I'm not going to talk about that right now, but I want to directly jump into the topic called DHT, distributed hash table. So what is DHT? I will actually using this idea instead of going through this text. Okay, let's look at this picture. So let's first look at the hash table. So what is a hash table? Hash table, essentially you provide a key to this hash table. It will actually determine which of the entry is actually representing this hash key is going to hash into. Okay, if you think about that, there's a hash table. This is not distributed, it's a regular hash table. You want the content. And this content has some kind of index. And that index could be a checksum, or that index could be a ISBN number, or that index could be whatever URL. So whatever information the application decides to map each of the content to a particular key, That is application specific, but you must have some kind of index key that you need to provide to actually use as a entry to the hash table. So in other words, if you actually want to watch a movie, you need to find out what is the index. For example, okay, in BitTorrent, the BitTorrent, you're going to have some kind of tracker number, some kind of piece number that could be used as index for you to actually be able to go look for that. Okay, so just a very quick survey. How many of you have learned how BitTorrent actually works, the BitTorrent protocol? A little bit, okay. Yeah, okay, I'll slow down when I see you might need to understand a little bit internal of BitTorrent. Okay, don't worry, thank you for letting me know. Yeah, I mean, you guys are very good. You never need to watch those contents, so you don't need to do BitTorrent at all. Okay, I assume that's the reason. All right, so here is the index key. So what is hash table is trying to provide is that I provide a key. That key, in this case, I said 160 bits. And I provide that 160 bits into this hash table, and it will hash to one of the entry uniquely. And basically, I'm saying that the content that's representing this 160 bits key is actually exactly at the entry I put in there. Okay, so that's what hash table, right? You give me the key, I give you the content. And for example, I give an example. This could be, the key could reflect to what is the GFS chunk. By the way, GFS is not using hash table, but they could use hash table if they want. It could be where's the piece of music and whether this particular BitTorrent piece is available. And you can think about that. There is a lot of things you can actually get out. The content sharing or a book or whatever you want to get. Okay. In fact, you can actually even do email. If you actually say your email address match to a particular key, and essentially that particular yellow box pointing to is your inbox that you can either deposit an email or retrieve an email. You can have a this kind of hash table based key. Okay, so that's HT. So let's look at what is DHT. It's very simple. It's a DHT is I just break them. I just basically have a huge table. I just break it into pieces. That's what distributed, right? So it's no longer a single place I'm holding the whole thing. I'm actually distributing. I mean, this is going to be unscalable because the table could be really large. So usually the way it works is that each of the nodes is hosting a portion of the hash table. Think about in this room, currently we have about 15 people. I didn't count, but roughly. About 15 people. So essentially you can see that we can arrange such that each of us handle a chunk of that hash table, which means that each of us handle the content being stored in that chunk of hash table. Okay, think about this. Then essentially, we can make a full hash table and its content distributed into this 15 computer here. And that's the basic idea of a peer-to-peer. We can break it using your hard disk, and our network bandwidth would be able to do certain things. Okay. And of course, because the people will join and people will leave, right? Some people will come in, somebody leave. So you will see that this hash table sometimes will shrink, sometimes will grow. And also you will see that some of us actually having a bigger chunk. And the thing is that the idea of peer-to-peer is not trying to say every one of the 15, we actually roughly, fairly sharing exactly the number of size of the hash table or the content. That's not the purpose at all, at least the basic one. Instead, we want to actually find the most efficient way, depending on your identity. Remember I said, when you actually started the machine, you actually need to have a peer identity. And then I can actually provide routability. So this peer identity is kind of random. It needs to be random. It needs to be random. So if the random of 15 identity in this room just happily uniform distribution over this whole hash table, then probabilistically, we could each have exactly the same size if it's a uniform distribution. However, random doesn't mean uniform, and therefore you will expect it to see some of us actually have more stuff than others. But that's actually just the nature of how things work. But overall, each one of us share, and you leave, you join, and things like that will be running okay. All right. So what I'm actually going to talk about is to go into the detail about how DHT really works. And there are multiple ways to actually implement or design the DHT. But I'm going to tell you a particular version of a DHT called chord ring. It's actually a ring topology, and it's actually be able to handle a lot of things scalably and also deal with the peer arrival and departure. And how do I handle different kind of failure in that case? Okay. Okay, so I want to talk a little bit about DHT. So essentially, now I'm actually think about what is DHT. DHT is essentially you give me a name or an index to the content you want, or the key. And I'm actually going to give you the value. So it's essentially a key value pair, just like a JSON. Okay, it's a key value pair in this story. So the first question I asked you earlier, how many of you familiar with BitTorrent, is that, okay, I want to actually tell you that how DHT is being used in BitTorrent. Okay, so I'm actually not have enough slides to talk about BitTorrent, but I'm actually going to basically just try to just using one slide to talk about this idea. Okay, so in BitTorrent, we have a concept called tracker. So what is a tracker? For example, if we want to share content, what kind of content you guys like to watch this day? Just pick an example. Some kind of drama. Okay. All right. Assuming there's a famous one, you know, a really good TV show or whatever. Assuming 20 gigabyte. Okay. Assuming 20 gigabyte, we want to share. So 20 gigabyte, obviously, you cannot have a one peer to have that. So everybody will provide some portion of that whole piece. But the idea of a tracker is try to find out which peer owns which piece. So we have a peer and pieces. So we want to make sure that which peer owns which piece. So that's called tracker. So the idea of the BitTorrent works is that when you join the BitTorrent, you decide to use this torrent file. The torrent file essentially gives you the two information. Number one is where's the tracker. Number two is all the checksum information for all the pieces that you're going to put together to have that video you want to watch. So essentially, there's two reasons. Number one, you contact the tracker, and the tracker actually gives you the IP address of all the peer that's actually participate this sharing. Okay, number one, the tracker will give you which IP address is online, which other peers online. They are actually currently either has the complete 100% of the content, or they have some part of the content. Okay, and once you actually get that, the second information is that now you use that information to contact other IP address to exchange that which piece I have, which piece you have, and then we can actually start communicate directly. Yeah.
So in this case of 20 file, the number of pieces would be huge, right?
Right.
And the file that is generated, say, which piece is where, that file or that table will be enormous in size.
Okay, no, I'm sorry, I didn't get that part clear. So the tracker will only tell the peer what are the peer IP address. Not where you have the piece, but just the peer number, just the peer and their IP address. Okay. So once you have that peer address, you actually select, you actually communicate with each of the peer about what's their availability, what piece they have. And then you actually collect that, and then you decide who you want to get what piece. That's how BitTorrent works. Okay. So BitTorrent, by the way, is not using DHT at this moment. I'm just talking about a simple tracker. The tracker is just collecting IP address, and basically you have the torrent file. You can verify whether the piece is actually indeed the piece you want. That's what BitTorrent is working on. Okay. Okay. Let me ask a question. If say you share that content, assuming on HBO, on Netflix, assuming that's actually really copyright belong to Netflix, how do I shut it down? How do I shut it down? Oh, by the way, there is one concept I forgot called seed. In BitTorrent, there's a concept called seed. So a seed is a peer that have all the pieces. That's called seed. Okay. So the thing is that you have to have some seed. Okay. Now I want to ask you, how do you actually shut down the BitTorrent? You know it's actually violating your copyright. How do you actually shut it down?
Disable the tracker?
Exactly. I just shut down the tracker because you have to have some place to put the tracker, right? And guess what? If I want to share a file, if I want to offer a tracker service, I have to include the tracker IP address and whatever in the tracker file, right? In the torrent file. So essentially, if you want to use BitTorrent, I want to shut it down. I just go to whatever the dark website or the Pirate Bay to actually download a bunch of torrent files. And go into the torrent file and try to find out where is the how do I say that? Where is the tracker? And I will just find a way to shut it down. That's why some of the websites got shut it down, because people actually collect those information saying that, hey, you are offering service. That's actually helping distribute illegal copyright information. Okay. Now we're going to see how DHT is going to help. I'm not sure in this case it's helping which side. Okay, it's helping the Pirate Bay side. Okay, so it's called trackerless BitTorrent. You might have heard about this. When you use BitTorrent, there is called trackerless BitTorrent. So what is a trackerless BitTorrent? Meaning that inside the BitTorrent, you actually don't have a IP address. All you have is a 160-bit key for you to actually relate it to that content. So the thing is, I want to download that movie, and that movie somehow created into the 160-bit key. And then I'm actually going to turn that 160-bit key, go to the hash table, and then try to find out that particular error I put in there. That's going to be my tracker. So essentially, the tracker belong to what? Belong to one of the 15 people here. So remember, I'm going to split this hash table to 15 of us. And the thing is that when you give me the key, 160 key, it's going to refer to one of us. And the thing is that on your computer, you're going to store the IP address of everybody want to actually contact you as a BitTorrent operation. So now the Netflix and HBO, now they realize, they look at the BitTorrent, and then they come in here and they found that guy. Okay, I blocked your IP address. That's okay, you're gone. This will be automatically shipped to, and I will show you how that works, automatically shipped to the next guy. Because there's no way they can shut down all the computer in a peer-to-peer system. This is called trackerless BitTorrent. I mean, technology is a neutral. I'm not promoting the scenario I was talking about, but in fact, that is a capability that you can actually be able to have a robust information sharing without a infrastructure using DHT. Okay, so you can see that DHT is very powerful. It's actually allow us to share something, and it has some property a centralized system cannot provide. Okay, all right. Any question before I move on to tell you the detail how this is going to be implemented? Okay. I'm going to directly into talk about chord. Okay, as I mentioned, I'm actually going to directly go to the picture called chord ring. For you to understand, instead of telling you all this detail, I want to directly go into this picture. All right, so essentially a chord, let me actually close this one because it's blocking me. So conceptually, a chord ring is a circle with number of nodes on the circle is power 2, some kind of power 2. So here is an example, it's very simple. I only have 2 to the 3, only have 8 nodes, but this could be easily become 2 to the 16 or 2 to the 128 to have a huge ring over there. So from the topology, this is what we call identifier circle. Means that, remember I said, when you want to join the ring or join the peer-to-peer, you have your identity. That identity could be your email address, could be something which is really unique to you as a participant. By the way, this is not the identity to the content, but this is the identity to yourself. And this part of computation is very important for you to decide based on your identity, where will be your location in this hash table. This is still a hash table, but the hash table now I kind of bend it to connect to a ring of power 2. Okay, so essentially you have to decide how do you act where you are. So this is an example, looks like this. You have 3 nodes. So totally I can have 8 nodes. But right now I only have 3 nodes because only those 3 guys, they actually be able to be online. So therefore, one of them is 0, one of them 1, 1, 3. The rest of them are just empty. Okay, nobody is here, but that's okay. So now I'm actually going to split the ring. Hold on. So I'm actually going to use this one. So essentially, because I only have 3 nodes, I have to chop my hash table or chop my ring into 3 different segments and give each of the segments to one of the 3 nodes. All right, so depending on where you are, you're going to get whatever node you have, and until you hit the next node. Whatever before that is actually going to belong to you. So you're going to be assigned to the hash entry where you currently map into, plus all the entry in that ring or in that hash table until you hit the next available node. And that's the idea. So for example, if somebody actually wants the content that's also key number 1, it will actually match to this node. And if somebody, oh, I'm sorry, it's actually not the node after you, it's the node before you. So, okay, now I see the example. But if you want, okay, say this is a node number 1. If somebody actually, now this 1 over here is a content key. It's a content key. You want this content, you map, okay, then whatever you want is actually node number 1. That's the first case. However, if you want 3, you want something, oh, sorry, if you want 2, the content key is 2. So you want, say, a Netflix movie, that's the key value for that movie is actually number 2. But the thing is that I don't have a node number 2 here. And therefore, who is going to respond for that? I'm going to actually store the information in 3. Okay, so essentially you can see that anything that's actually 4, 5, 6, 7, and 0 will go to 0. So let me actually just say it very quickly, is that I actually split the ring into 3 parts with the 3 nodes. And depending on where you are, the first part is going to be just 1. The first part is 1 node, is 1. And 2 and 3 will go to 3, and 4, 5, 6, 7, and 0 will all go to 0. So that's the way it's a ring for me to actually cut it. So now I have a core ring with 3 segments. So if now let's go back to trackerless BitTorrent. If somehow the torrent file I want to download map to say 6, okay, so when I do the hash, I realize the hash value is actually node number 6. So which node is going to be my tracker? 0, right? Because that's the next node that's going to host all the information. So you can see that it's a little bit unfair for 0 because 0 actually handles a big chunk of that key space. So therefore, all the content that's related to 4, 5, 6, 7, 0 is going to store in 0, that node 0. Okay. Okay, so now we're going to talk about join and departure. So I remember people like to join, people like to leave, and well, how do we actually be able to handle that? So let me actually take a look at this. So for example, I have a different kind of content now it's distributed like this. For example, node number 1 has 1 key, node number 3 has the 1 key, that's 2, because there is no content mapped to 3, and node number 0 actually have a 5 and 7, right? Has 2 keys, assuming that's the case. So when you have another node that's actually coming in, looks like this. So essentially what we want to do is that we want to actually shift the content to 5. We want to actually push. When you actually realize somebody joined, then essentially what you need to do is you actually find a way to actually push the content you have. So you're not going to do this all the time, but you do it when somebody joined, you actually run the protocol. And by the way, you also need to periodically run the protocol because sometimes you don't know somebody already left the ring or somebody actually has some dynamics. So you actually have to construct to do like this, and eventually you have this. And similarly for departure, assuming this is where we are, and node number 1 is gone. So before node number 1 is gone, you should push the content to 3, and such that after that, this is joining. Okay. So that's actually a kind of nice way for you to understand it's a ring. And depending on the join and departure, the information got shipped from one part to the other part. And it really worked well this way. Any question? Okay. So let's actually look at this. What kind of information that we must contain in this join departure business? So I want you to actually think about this picture. What kind of information I need to actually maintain every time, anytime that some member left the ring or some member joined the ring? What kind of information do you think is relevant or important? Obviously, we need to know what is the piece, what content we have. So it's content part, we already talk about that. But there's another piece of information that's important for us to maintain in this ring. What? How many nodes? But probably more important, how many nodes? Because it will change, right? Somebody joined, somebody left, -1, +1. But you actually hit something similar, is that who will be my next neighbor? So essentially what we want to maintain is that where is the next node that I need to worry about? Because the thing is that when we do this computation, if you look at this picture, that how do I actually know if I want to find some content, that content is actually being stored in node number 3? So think about that. How am I actually going to be able to find it? What is the IP address of 3? Remember, this is not BitTorrent. We don't have a tracker. Nobody actually tells us what's the IP address. Everybody joined with just a key that reflects your identity. How do you actually be able to actually find number 3? So therefore, the information is important, is that we need to remember who is our successor. Who is our successor? Who is the next node that we need to worry about? So in other words, because any one of us, because peer-to-peer means that we are part of it, right? So meaning that we are already in this ring. We're one of them. We're one of them, but I want to find the other one. So you are one, you want to find the other one. So how do I actually find it? I know I want to find the node with index 3 or whatever number I'm looking for. So assuming I'm 6, I'm actually currently 6. How do I actually get to 3? And I actually don't know the IP address, because I said this ring could be really huge. It could be 2 to the 128. And it's a huge, that means I cannot actually remember all the IP address, and it's hard to track. And the basic idea is that I need to know who is my successor. So the thing is, the 6 only know the next node is a 0. And 0 will know the next node is 3. That's his successor. And the 3 will know the next node is a 6. So essentially, the search worked this way. I want to find 3 based on the content. I'm actually 6. So I'm actually asking my successor, is this your responsibility for handling index 3? And the 0 will look at it and say, I'm sorry, I'm not, because between 0 and 6, there's no 3. So 0 need to forward it to the next successor, which is a 3. And then it will ask him, hey, 3, are you handling this piece? 3. And 3 will say, okay, great, I handle it. And then at that time, the 3 will directly communicate with 6, because that was the search. Because when I issue the search, I'm actually sending with my own IP address. So 6 to 0, 0, 4 to 3, and now 3 actually confirmed, I have this piece. So 3 now contact 6, saying, hey, let's actually exchange. Does that make sense? That's how information is maintained in this system. Remember, there's no infrastructure. And you don't want infrastructure, by the way. You don't want like a tracker kind of system get shut down. You want to be able to just know who is your next neighbor, and then to build this up. Okay. Any questions? So that's why it's important for you to understand the basic idea. Pointer to successor and the content itself. Yeah.
So could be a little bit less efficient if, let's say, there are several peers. There are two in California, but the first one joins first, and then another one in probably Wisconsin joins, and then so they kind of know how to contact each other, and then another one in Florida joins, so they sort of like they know how to contact. But what if now another peer in California joins, and the original one wants to contact the other peer in California, and so this one in California needs to contact Wisconsin, and then to Florida, and then to
California. Go around, right? And then we find it.
So that they cannot shortcut to some extent.
Okay, this is a great question. We're actually going to talk about how to shortcut.
Okay.
There was an algorithm to shortcut, but I want to go back to your question. You are kind of alluded to a scenario of caching. I'm trying to caching the relationship between me and the previous peer I'm actually communicating with. That might be an optimization, but just be careful because we cannot guarantee which peer has what content. So in that sense, that California, I actually communicated maybe 10 minutes ago. Because new node joined or departure, he might actually lose the content he is actually managing. He might actually move it to some other successor or things like that. So essentially, the peer-to-peer system, you might be able to do some kind of like a caching because previously you won't, but just be always careful that you need to verify whether that peer still have the content you're looking for. But we're going to talk about a algorithm to actually be able to make it faster. Like what you said, I don't have to go to Florida, Wisconsin, and then California again, even though I'm actually already in California. Okay, by the way, peer-to-peer system, the general one doesn't worry about locality, which is a feature or is a waste because sometimes you try to contact some peer that's actually very far away while you actually have some peer that's locally. So that's kind of optimization we have to add on to actually provide a better performance. Okay, so I'm actually going to do this way. Okay, so this is, I'm actually make the ring a little bit bigger, 64, right? This is probably 64, yeah. This is a 64 ring, and you have about maybe 7 or 8 nodes or 9 nodes in this picture, right? So that's the ring. And the worst case, if you're in node number 8, you want to look for something for node 56. And this is the path you have to go through. You have to go from 8 to 14 to 21 to 32, 38 to 56. So essentially, your search time is going to be O of n, linear to the size of the number of nodes in this ring. Okay, by the way, there is a 2 number, which is a lot of paper when they talk about peer-to-peer, they actually didn't distinguish. There's one figure called size of the ring. The size of the ring in this case is 64. 2 to the 8, 64, because there are 68 possible nodes that you can have. And the other number is called number of nodes that's currently in this ring. So the ring size is 64, but the participant size is really only 8 or 9. So the thing is that there was actually one very famous paper who made this mistake. They said the search algorithm of this is linear to the ring size, which in this case is 64, which is maybe good approximation in some case, but in general, the search need to be linear to the size of number of nodes that's actually there. Could be in today, any kind of reasonable large scale peer-to-peer system, the ring size usually much, much bigger than the number of nodes. Because if your ring size is not big enough, you're going to have a hash collision, very easily, which is actually going to be, you cannot uniquely place everybody. That's going to be a trouble, okay? So this is the issue that I think you point out is basically take a lot of time. Okay, so I'm actually going to tell you how to actually do this better. I'm going to introduce something called finger table. So finger table is a very useful concept in peer-to-peer system. It's essentially providing a routing table to different sector of the ring, sector by power of 2. So what you have is this. If you look at the finger table, it looks like this. So I can actually separate the ring table over the following section. The first section is 2 to the 1, distance from me. The second section is 2 to the 2 and 2 to the 3. If my ring has 2 to the 64, then my finger table is going to have a 64 entry. So essentially, your finger table is actually to the logarithm of your ring size, not number of nodes. Okay, again, just make sure the ring size and number of nodes is different. So essentially, that's what you have to n plus 2 to the I. So essentially, what it does is saying that instead of just know who is my next successor, I want to know all the successor that's actually handling that particular segment of the table. So let me give you an example. Assuming I have things like this. Are you doing anything? Ah, coming. Okay, so this is the ring table. Let me actually show you ring table for both no number 0 and no number 2. Oh, no number 0 and no number 1. So in no number 0, we can see that its current position is a 0 plus 0. So it's a 0 plus 2 to the 0, 0 plus 2 to the 1, 0 plus 2 to the 2. So there are 3 entries. Why is there 3 entries? Because this is 8, size is 8, is 2 to the 3. Okay, so you have 3 entries. And what this does is that for each of this 3 entries, I actually have a what I call a starting point. The starting point is 1, 2, 4. In fact, that starting point corresponds to that 3 number. Okay, I'm just using a number instead of saying 0 plus 2 to the 0. So you actually see this 1, 2, 4 represent that 0 plus 2 to the 0, 0 plus 2 to the 1. Okay, and then each of this essentially represent the content that you're interested at the beginning of that power 2 section. And then for that power 2 section, I want to know who should be the successor. So the key idea is that I separate my whole ring into this power 2 sector. The more, the bigger. And then I actually want to know who is the first successor in that sector that's going to receive my request. Because if you want to actually access that section, you must actually reach the first successor. So that's why you have that. Let me actually give you another, let me go over this. For example, the first one is actually starting with 1. And if you starting with 1, of course, your successor is 1 because 1 is available. And then the second one is start with 2, and we know that the successor is 3. The third entry is a 4, so the successor has to be 0. So that's the successor. Why is successful useful? Is that now instead of for me, for example, I want to look for content number 6. Let's pick content number 6. Previously, I have to go to 0 to 1, 1 to 3, and then 3 to 0. And then I can get to 6. But in this case, 1 already have a successor. You can look at the last one. this entry here, it basically say, if you want to get anything that's actually larger than 5, you go to successor 0. So essentially this one, when he wants to get 6, he realized 6 is bigger than 5, and then he will directly go to here. So that's essentially we're doing a what I call a binary search. You think about that, this is binary search. Okay, we split in the power 2, we'll be able to jump. So you instead of linear to the number of nodes, this one is a logarithm to the size of the ring. Okay, so this is the improvement. So from linear to the number of nodes you have to the power, logarithm to the size of the ring. All right, so the complete table will look like this. But now I'm actually going to tell you the real table looks like. So previously, remember, we want to get to 54, right? So instead of go through every single node, that you look at your table. You look at your table, you're in node number 8. So it's going to be 2 to the 0 to 2 to the 5, because this ring is what? 2 to the, this is 64, 2 to the 6. Yeah, 2 to the 6. That's right. So you look at this, you're looking for 54. So you will find out that it must be after this one. Wait a minute, where's 64? Where's 52? I'm confused a little bit, sorry. Let me actually check. So we want to look for 64. So 54 must be, okay, the last entry, right? 8 plus 32. Because 8 plus 32 is 40. So it's actually, it must be M42. So I'm going to use the 5th entry. So now I'm actually going to connect over here to M42, the next hop. So immediately I jump everything before M42. Okay, remember, M42 also has a finger table, just looks like this, but instead of 8, it's going to be 42 plus 2 to the 0, 42 plus 2 to the 2. So actually, why don't we actually do this for everybody to actually see which one we should be looking at? I'd like for you to do a little bit of exercise. So now it will be 42, 42, 42, and then 42, right? So now we know it's a 54. So if 42 plus 2 to the 8, 2 to the 3 is 8. So this is a 50, and this one is actually 58, I believe. So the thing is that you actually want to go to 42 times plus 8, which is 50, which is M50. You want to go to whoever is the first successor at or after 50. So that's why you actually find this one. What's that number over there? Oh, I cannot see this anymore. My eyes hurting me. Okay, so that's why we're looking at anything that's bigger than 50. Is that 51? Yeah, that's 51. So you don't have a 50, so the next one is going to be 50. And at 50, you again will have the table from 2 to the 0, 2 to the 1. And just in that case, you realize that is actually exactly it. 56. That is actually half the content 54. So by doing this, you actually save a lot of time to make a linear to the logarithm. Okay? All right, I'm actually going to, I don't have time to talk about this chameleon. You know what? I'm actually going to stop here. We have about 6 minutes. I think this is a good point for us to stop to understand. So today, I mainly communicate two concepts. The first concept is what is a peer-to-peer system. And the concept is instead of having a centralized managed facility, we rely on each one of us, 15 of us, contribute some resources and we share. And we'll be able to share a lot of information. And there's a lot of good property about this kind of sharing that we can protect our own, say, privacy or protect our own vulnerabilities to certain issues. Of course, we expose ourselves to other vulnerabilities as well. That's the first thing. And the second thing I communicate to you is the most popular concept in what we call structural peer-to-peer system, which is DHT. So what is a DHT? Why I said DHT is a structure. So if you don't have this structure like the DHT, then you either need to have infrastructure to help you to identify where are the peers, or you're going to do flooding. In fact, some of the earlier peer-to-peer system, they have to do flooding. What do I mean flooding? You actually broadcast in the network to your local neighbor, say, hey, who has this content? And they will help you to further propagate. Just like what I did a little bit when I have this David social link, the way we do search is a flooding. So structured peer-to-peer, in fact, is the only peer-to-peer system that's actually going to be scalable to a large number of nodes in the internet. And the way you handle that, one of the most popular idea is called core-ring. So essentially, you do this kind of hash computation, and we let each of the nodes to actually handle a segment of the hash table. And this is going to be dynamic because people will join, people will leave. So that's a very important property about such a structured peer-to-peer system. And we kind of, together, 15 of us, we basically represent a nice framework for us to be able to communicate with each other. The final point about the DHT is this concept called finger table. So the finger table is just helping us to be able to more efficiently to identify the peer that's actually have the content we're interested in. Of course, the drawback of finger table is that to manage the content of the finger table will actually needs a little bit more time, because when somebody leaves, I actually need to recompute the finger table. And actually not just recompute one node, you have to recompute a lot of nodes in that sense. Okay, so the computation is more expensive when you maintain that finger table. But once you maintain, then you can actually, so essentially this kind of system will work well if the membership is relatively stable. If it's not stable, I mean, one of the issues, internet is not stable. You will see your peer join in and out. Then the way peer-to-peer system deal with that is they will put some reputation. If this node has a bad reputation, because it's not saying they're a bad person, it's just their internet connection or their availability is very unstable, and that node will actually be ruled out to participate as an infrastructure node. And they can still access the node, but they won't be able to be hosting content. That's actually a lot of optimization people actually develop. You can imagine, just want to make sure that we will be able to have a stable infrastructure to do that. So that's called a structure, because you have a organization to put everybody in a specific location in this DHT. Okay. All right. I'm going to stop here. Any question from remote? Hello? Sure. Hold on. Let me turn off first.